3, 4, 5. And we got position 1, position 2, position 3, position 4, position 5. Now let's go to the heap. There it is. And we see in the heap that we have node 5 at the top. Node 4 is in the second position. Node 7 is in the third position. Node 8 is in the fourth position. And node 6 is in the fifth position. Everybody okay with that? All right. So the heap, this is a binary heap, and we've got the positions. Let's come with the red. I'm going to write down what the key is. So 1 is in the 1 has node 5. So let's go to mode 5. Here it is. And 5 has key 12. And no. I'm looking at this. 5 is in the top. Why isn't 4? Wait a second. I'm looking at this. Delete min, delete 5 is 12. Oh, neighbors are 3. I'm just looking at this and it's not making sure that I see that this is a bit worried about this 12. Cos 1, 12. Cos 2. Let's have a look at the positions. Position 1 is 5, and that's 12. Position 2 is 4, and that's 13. Okay. So position 5 is 12. There we go. Position 4, there it is 13. Position 7, which is infinity. Position 8 is infinity. And position 6 is infinity. Okay? So there's the, this is the heap at this point in time. We do a delete 3. So I'm looking at this, we haven't done the delete. I was wondering why it's wrong. Bing, bing, bing. We're here. Let's have a look. So 3 is at the top. So give me a second. Let's go, we've got to do the delete. Here we are. See, I want to do the delete. So let's go back. The heap is 6 at this point in time. Oh, 2, 3, 4, 5, and 6. Oops, it's horrible looking. Circle. 6. All right. 3 is at the top. 5 is second. 7 is third. 8 is fourth. 4 here and 6 here. Everybody okay with that? We're about ready. So we're ready to do a delete. We do delete 3. So how does this work? 1, 2, 3, 4, 5, and 6. Well, delete 3 is we kick 3 out. So 3 is the one that we kick out. Okay. I'll put it here. And we move 6 up. And so we move it to there. Well, let's put in the values that we've got for this. So the key for 5, let's do values in red, is 8. The key for 2, the key for 5 is 12, sorry. The key for 5 is 12. Here it is, 5. 5 is 12. The key for 2, 5 is 12. The key for 7 is infinity. The key for 8 better be infinity. The key for 4 is 13. And the key for 6 is infinity. Why is the key for 7 infinity? 3, 5, 7, 8, 4, 6. Did I do the heap right? 3, 5. Position 1 is 3, is kicked out. And we have 5 and 7, 8 and 4, and 6. Right. Are you all good? Got a thumbs up? So the heap looks like this? Coming from a homework question? Yes? We have an agreement that the heap here, just reading them off, 3, 5, 7, 8, 4, 6, and we've moved 3 out. So 6 itself is infinity. There we are. So I've moved 3 out. So 3 has now become part of the spanning tree. And now we notice that this 6 unbalances the heap. So what we have to do with the 6 is move it down with the smallest child. So the 6 is going to move down here. Well, let's do this in green. So I'll go over this step one more time, just to show you what was going on. So originally, I have 3 and the value of 3, just for the point. Okay, we have 3. And now we're going to kick 3 out. So 3 was the original quote. 3 has 9. 9. So this is a min heap. And everybody okay with this? All right. So I drew that. Now I'm going to kick 3 out and move 6 up. So I'm going to kick 3 out and move 6 up. And this is infinity. So let me do the green. This is a problem because it's no longer a min heap. No longer a min heap. And so we have to move 6 down with the youngest child. There it goes. And then becomes infinity here. And then we still got a younger child, which is 13. So we're going to do that flip and that flip. So what that means is that we're going to get a new looking heap that looks like this. 5 will now move to the top. 4 will move to the second position. 8 stays where it is. 6 is gone. Remember, 6 got crossed out, moved up, so it's it. And then we got 7. And we have this picture. We've got better have one more node. And here goes 6, moved all the way down. Let me put the values in. 5 at the top has 12. 7 stays at infinity. 4 is 13. 8 is infinity. And 6 is infinity. Yeah. So we've got this picture, oops, where the 4 and the 6 flipped. And then the 6 came down here, and it's infinity, and the 4 is 12. So if you notice, you see infinity, 12, 13, the infinity is going to come all the way down. It's a kind of rotation. If you think about this, this effectively created a rotation like that. Okay. So the 6 came down to the bottom. The 4 moved to the 5 position. The 5 moved to the top position. Everybody okay with that? We get these rotations. So what happens? We get these rotations that make it a min heap again. Min heap. And so we rebalanced, and I've got the we now got the tree, and now we have to update the neighbors. Okay, well, the neighbor of 3 is just 5. There's only one neighbor of 3. So what we're looking at, let me try and show you what's going on now. If we got the picture, we've deleted 3, and it's coming in. It's in the tree. It's deleted 3, and we have one neighbor. I'll do that in orange. Neighbors in orange. It has one neighbor. Maybe make it green. And the neighbor is 4. So the 3, if we look at the heap, the key for node 3 is 9. So currently this is 9. And the key for node 4 is 13. And so the question is, here's the neighbor 4. If we go through 3 and then add up this distance, 3, 4, do we get a cheaper distance? Okay, well, node 3, 4 is right here. We've got neighbor is 5. We'll get it right. Neighbor is 5. Here we are, put it over here. The neighbor is 5. And the weight is 4. So the weight is that distance. Remember, the weight is STW. Okay, so that tells you it's 4. Remember, this was STW. So S is 3. There's the S. T is the neighbor. So that's 3 to 5. 3 to 5 is the weight, W, is 4. So I'm reading off that information here that we've got. The vertex we're looking at is 3. The neighbor is 5. And the weight is 4. And we get that picture. How does that look? Thumbs up? Yes? No? I don't see any responses one way or the other. Okay. We're going to see, I've got a mistake here, I think. So it's 12. Let me rub that out. This is 12. apart from the mistake, is 12. And let's see, 9 plus 4 is 13. If we go that route, and so we see exactly what I wrote here. The distance to 5 is 12. Check. The distance to 3 plus the weight from 3 to 5 gives you 13. Check. And so no update. We only update the distance if we do it. Let's move on to the next one. So we got this is now the state. We've got this as the tree. Let's rub this out. We don't need this anymore. And we repeat the whole cycle. So delete min is going to delete 5. Let's go ahead and do that. 5 is kicked out. We know the routine now. This is the heap. 5 is kicked out. 6 is moved to the top. 6 with its infinity is moved to the top. And again, it's unbalanced. So there's the tree. We've deleted the top node. We move 6 to the top. We all okay with this? Just kick out the top node and move the bottom right to the top. It's now no longer a min heap. And so we have to rebalance it. So we look for the cheapest child. Here it is. Goes to the 6. And that's it. The next one down is infinity. So it's just simply that. So we'll go ahead and we will ignore it. We got that. We have that. We have that. We have that. This is 8. This is now 6. This is now 7. And at the top, we got 4. And we've got, this is 13. 6 is infinity. It's not a very great example. I don't know why I picked this one. Okay. So we deleted and we're left with, let's check that the tree is what we think it is. Let me see if I can move this over. It says 4, 6, 7, 8, 4, 6, 7, 8. So when we delete the nodes out of the tree, this is, remember, we've deleted node 5 out of the tree. And when we delete node 5 out of the tree, we get this tree. So node 5 was the deleted node. We're looking at 5 was the node that was deleted. So now we look at the neighbors of 5. So we've got this picture. The neighbors of 5, got 2 of them, that's green. The neighbors of 5 are 6 and 7. And the weights are 4 and 4. 4 and 4. The weight of 5 was 12. So the weight of 5 is 12. And we've got 4 to 6 and 4 to 7. Again, we're going to check if by going through 5, so let's go ahead. This is coming from the root. So let's have a look. The distance to 6, the neighbors are 6 and 7. The distance to 6 is infinity. If we go through 5 and then add the weight from 5 to 6, we get 12 plus 4 is 16. So this is, we got infinity here and we got 16 here. Obviously, 16 wins out. So we're going to change 5. We're going to change 6. Here it is to 16. There we go. It changes to 16. All right. update distance 6 to 16. Let's have a look. We've made it 16. Is it still a min heap? Let's have a vote. 13 here, 16 here, infinity, infinity. Is it still a min heap? Can we have a vote? Some thumbs up? Something? Yes? No? I can't see everybody. I should change. Let's see. Let's click on this. See if I can get a bigger view. Oh, some thumbs up. Got 2 thumbs up. Great. Okay. But it's still a min heap, so we don't have to push it up. Let's do 7. 7 again is infinity. 12 plus 4. Let's go. I got the, let's go to the. Here it is. Distance to 7 is infinity. The distance to 5 plus the weight is 16. So obviously this becomes 16. And again, doesn't have to push up. We didn't have to change anything. Okay. One more step. One more to go. I hope that's no update. This is not a very useful one. Let me just say something. Let's pretend for a moment this is not 13, but this was, let's give it a new value. Let's pretend that this value in here was 18. Then 16 and 18, we would have to switch these around. Do you see? If in the tree, we do the update and the update results in the new node, updated node being smaller, we would have to change it around. So in other words, we would get 6 at the top with 16. Then we'd have 4 come down, and that would be 18. Then over here, 7 is 16. That'd be 18. Oops, make it red, 18. And we still got an 8 hanging out. And that's infinity. So you get the idea that when you run this, so I'll go through the steps again. So steps, oops, more. Make it black, steps. Draw the picture again. You got the smallest node at the top. That's kicked out. Let's call that M for a moment. You look at Nate, okay, you move this one down. And then in order to balance out the tree, you sift it down so it's descended to the right spot. Okay, then what we do is we look at the neighbors of M. Tree, and we update distance. So let's suppose the neighbor is V. So here's a neighbor. It's V. Neighbor is V. I'll make it nice. V. There we are. Then to update the distance, we may need to sift it up the tree so it climbs up to preserve the min heap. And I will leave, I put one of these on. I'm not quite convinced this is the best one to leave on for you. I'll put one up here, one of these annotated that you can go through. I'll leave it and you can check as I did here. If you take one of these boxes where you've done a delete min, here, the delete min, and you run it all the way through until you've updated the distances to the next delete min. Here we are. So in this case, we did delete min 2. It has neighbors 3, 4, 5. So the first thing we did, if you look at the, let me erase this, edit, make sure I'm in the right window before I do the erase, edit, remove notation. Okay, so here's delete min 2. This one's a little bit more complicated. That's why I didn't do it first. But let's have a look at delete min 2. So first of all, I go to the tree just before, then I have to go up just a second to look at the current state. We got 1, 2, 3, 4, 5, 6, 7 vertices. So 1, oopsie. That 1, 2, 3, 4, 5. We are getting some background noise. 6, 7. Is that me? Okay. So let's read data. 1, 2, 3, 4, 5, 6, 7. Position. Okay, 2 is at the top. 8 is second. 3 is third. 4 is 5. 5 is 6. 6 is 6 and 7. They're in the same position. Let's put the distances in. So 2 has distance 8. 8 has distance infinity. 3 has distance 4 infinity. Hey guys, we've got some noise coming through. 5 has infinity. 6 is infinity. Everybody's infinity. So yes, this is okay. Everybody agree? This is a min heap. And look, you saw how I read the data off. I read off the heap, looked at the vertices from the heap, and was able to read the keys. So we got that picture. Now we're going to delete 2. Remember how we delete 2? We're going to take out 2. Here it goes. So 2 has been kicked out. We move 7 up to the top. It has infinity. Now let's take the green. We see that this is not a min heap, so we're going to move this down. Exchange here. So we get 8 to the top. That's what. Is 8 infinity? Did I remember? It's the wrong one. Boom, 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 boom. It's this one. Here we are. All right, so that's wrong. And so we get 3, 9, and 7 infinity. So this becomes 3 with 9. And this becomes, the one below becomes 7 infinity. There we go. So now we're ready to look at the neighbors. Let's come back up here. If I draw the picture over here, we remove 2, which had distance, by the way, of 8. And the neighbors, 1, 2, 3, are 3, 4, 5. The neighbors are 3, 4, 5. And we've got 9, 4 is infinity, and 5 is infinity. And the weights, 2 to 3, 5. The weight 4 is 5. Going to 4 is 5. And this one is 4. And what we do for each one of these is that we're going to update the distances. Obviously, this is 9. This is 8 plus 3. That's 13. That's no change. 13 is not smaller than 5. And there it is. I've written it down here. No change. Move down to the next one. We're looking at 2 to 4, which is 8 plus 5. That's 13. That is a change. So 4 is going to become 13. Now, we look at the parent of 4. So we've updated 4, and we look at the parent of 4, and you see that we're going to have to make a change. We're going to go ahead, and we're going to swap the 4 and the 13. You just draw it like this. You're going to swap the 4 and 13. And so I'm going to end up with, draw a picture. Oops. I'm going to new picture. 3 goes there. 4 goes there. 8 goes there. This side, there's no change. We get 7. And we have 6 going down. And we have 5 going there. So 8 then sends down infinity. 5 is still infinity. 6 is for infinity. 7 is infinity. 3 is 9. And 4 is 13. Note, if this number was smaller than 3, it would go up 1 more. But 13 is bigger than 9, so we won't do that. Okay, so that's 13. Let's have a look at 5. We've got 8 and 4 is 12. Oops, do it there. 8 and 4 is 12. That's smaller. So 5 is going to become 12. There we are. 5 is going to become 12. And look, 12 is smaller. So we're going to do one more flip like that. And we're going to have 5 move up to where 4 is, and 4 will move down to where 5 is. So I'll just put them in place. 5. Oopsie. Black. 5. And it's going to be 12. Put red in for 12. And this is 4 and 13. All right. So we get 4 and 13 there. Rub it up. Black. 4 and 13. Oops. So you can see that what's going on in the heap is a bit jumbled up when we look at it. We can't guess what the heap is going to look like, except the smallest value is always at the top. Let me just check that this is matching up with what I was able to do. Here we are. So this is the last one. So the heap is 3, 5, 7, 8, 4, 6. Yep, we got the heap is correct. Our analysis was correct. We end up with the heap is correct. Okay, so probably what I'm going to ask you to do in homework is you start at one point and come down to here. Just do one full cycle of the process. Well, let me finish off with some fireworks for the last part of the I'm going to run, and I don't know. Let's see. Right. I'm going to move this over. And to show you how well the algorithm works, I got a slightly larger graph. So a plot graph, there's the graph. So we're looking at this particular graph. I'm going to run actually Prim's algorithm. Prim's algorithm is the same. I'll explain on Monday. It's the same algorithm, except you don't add, you only add the weight, the cost at each step. And what we get when I run this, here it goes. You're going to see it's going to add the cheapest edges as we go along. They're connected because remember, you're looking at the neighbors as it goes along. And there we are. This is the spanning tree and the cost is 36. Let me just spend just a couple of minutes explaining what the difference is between Prim's algorithm and Kruskall's algorithm. Let's bring this down. All right. Edit. Insert new page. Bump. Edit. New blank page. The idea between the two is, as I said, you've got a spanning tree in both cases. Maybe a different spanning tree. We'll do that one. Then we got the neighbors of the vertices in the spanning tree. Same thing here. We have neighbors of the vertices in the spanning tree. These would be actually looking the same. So in both cases, we have a spanning tree and the neighbors of the spanning tree. But what the difference is, we are looking at cost of getting here. So that's the total cost of going from the root node to the vertex that we're studying. And we got these costs in the priority queue, and we choose the cheapest one. For Prim's algorithm, we only need, so this is the cost, but in this particular case, this is distance. In this case, we're looking at the cost. So only the weight, if this is U and this is V, we're looking for the weight UV. So notice the difference. In Dijkstra's algorithm, so the update is dist of, if this is U, this is V, and this is U, we looked at dist V and compared it with dist U plus the weight of U to V. So that's the total cost of going to U plus that stuff. On this side, we just look at the weight. So we got the current cost of getting to V as opposed to the weight UV. And this is smaller, we update with this. So cost, if this is smaller, we make dist of V equal to the dist of U plus the weight of UV. And this is, if this is smaller, we make cost V equal to the weight, or W. W UV. So what you're doing in this one is adding the cheapest edge each time, the cheapest edge that's available to us. We're on this one, so this is cheapest edge. Sounds familiar. Kind of remember cheapest edge in priority queue. This one is cheapest cost, distance, cheapest distance in priority queue. So notice the only difference between the two is this has got dist here, it has a dist U, and here there isn't a dist U. It's just WUV. So the code for the two algorithms is exactly the same. What they give you, of course, is a totally different spanning tree. And let me bring this one back over again, because this is.
Which side is prim and which side is Dijkstra left or right?
Can you say that again? I didn't quite.
It's the left one or the right one, Dijkstra or prim?
This is Dijkstra. Cost, distance, this is D Dijkstra. This is the one we just explored, where you did distance plus the weight. And if it's smaller, we update. In Prim's algorithm, you compare the cost of what you've got in the spanning tree to the weight. In other words, is this cheaper? Go ahead and put it in. See, so the cost may be that you got to V. Let's do an orange one. You got to V originally, it's this neighbor, we'll call that one X. And this gives you the cost. The orange is the cost. But then when we go through U, we find a cheaper cost. So if the cost, the weight is smaller than the current cost, I'll put that cost in orange so you can see. Cost of U V. So the current cost of V, here it is. And then we've got U, we've now introduced U into the picture. And if this is cheaper, because it's nearer, we'll put that one into the tree. So that they're exactly the same, except this one small step. And so the algorithms are exactly the same. Let me run this again. Let's bring it over. Maybe I'll just make I'll just do the pause a little bit more than, I got half a second here. See if I can pause it up. Let me. Here's Prim's algorithm. And it's right here. If the cost of V is bigger than W, W is the weight from U to V, there we are, W is the weight from U to V, then we update. That's it. That's the entire thing. We got a cost of adding vertex V in the minimal spanning tree if the new cost is smaller, and then we bubble up, just the same as we do for Dijkstra. Let me run it. Prim's demo. Run. Let me close this or let's close. Hang on. Boop, 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 boop. There's a close. Let's run it. Continue. Let's bring it over. I'm just going to make it a bit smaller. The monitors have different sizes. Here we go. Plot graph. So let's plot it. Let's run prim. And you see it's adding the edges, which are neighbors, cheapest ones available to us. And there it goes. Pretty nifty. It'll, of course, run much, much faster than this, but it's pretty nice. Maybe on Monday, I'll slow this one down to show you what the neighbors look like and which one we choose. But that's it. Prim's algorithm, Dijkstra's algorithm. I'll set up the homework. Homework will have some nice heap stuff, some Dijkstra using a table, which was pretty easy, and then either a Dijkstra or Prim algorithm using a priority queue. We're moving on to dynamic programming. That will be next. I like this Zoom class. I'm thinking we'll have a Zoom class the Friday before Thanksgiving break. I think that would be a great time to have a second Zoom class. All right, see everybody on Monday back in class. Don't forget a TMQ. All right, any questions?
Thank you. Bye.
Hope you
Thank you,
enjoy.
Professor.